In this section, we're going to talk about motion along a line. And so for all of these problems, or at least most of them, we're going to be talking about a particle moving along a line. Its velocity is changing, its position is changing, maybe its acceleration is changing, and we'll be able to figure out a whole bunch of information. But first, I want to write down some notation that we're going to be using all the time. The first thing is when we have the function s of t, this is kind of like f of x, s of t is the position function. That the s will represent position. I think in like Latin, we looked it up at some point. Somebody asked about it. In like Latin, position or something starts with like an s or something. I don't know. But s of t will denote the position function. T is going to be time, and mostly for us it'll be in seconds, but it could be in any like hours, minutes, or whatever. But if you plug in a certain time, then you'll find out where the particle is along the line. So like it's going to be on a number line. The particle is going to be always traveling on a number line, usually. And if you pick like time 0, if the particle starts at the origin, then at time 0 it hasn't moved at all. Then you plug in 0 for t, you get out 0. That's just one example. It's not always the case. And if you plug in like a different time, you'll be able to tell how far the particle is from the origin, like where it is on that number line. The particle can move backwards, move back and forth. So s is the position function of the particle, the position of the particle. If we take the derivative of s of t, that would be a rate. I mean, we can think of derivatives as rates. We already thought about that. So ds dt is the rate at which the position is changing. Like, how fast is the position changing? Another word for that is velocity. So if you take the derivative of the position function, say you have like an actual function definition, if you take the derivative of the position function with respect to t, then you get the velocity function. Isn't that neato? If you plugged in a t value, say you plug in like 5 for t, then at 5 seconds, you plug it in, whatever comes out. That's the velocity of the particle at that time. The velocity could also be changing, getting faster or slower, and going forwards or going backwards. Velocity has a speed and a direction. So when they say speeding up, they're not talking about velocity. They're just talking about, is it going faster or slower? When they talk about velocity, that includes direction. And we'll get more into that, but it'll be good to write that down. So velocity includes direction. If the velocity is positive, that means the particle is moving forwards. If the velocity is negative, that means the particle is moving backwards. So if you have a velocity that's like 20 units per second, then that's moving forwards because it's a positive 20. If you had negative 20, it's the same speed, but it's moving backwards because it's negative. Hopefully that makes sense. And if you take the derivative of velocity, dv dt, then you would get the rate at which, sorry, not position, the rate at which the velocity is changing. Another name for that is, you'll guessed it, or you didn't guess it. It's acceleration. If you have a positive acceleration, that means the velocity is increasing. It's getting bigger and bigger. It means the particle is moving faster and faster. So if acceleration is positive, that means the particle is going faster and faster. If the acceleration is negative, actually, that's not strictly the case. If the acceleration is positive and the velocity is going backwards, then it's actually slowing down if the velocity is negative. But we'll get into that. We'll write some rules and we'll talk about it in class so it's completely clear. That's going to take some getting used to because there's not one strict rule where if acceleration is positive, then you're speeding up. It's not always the case because the particle could be going backwards. So we'd have to, if we're talking about like speeding up or slowing down, then we'd have to talk about both velocity and acceleration because remember, velocity includes a direction. And when you say speeding up or slowing down, that doesn't include a direction, so we have to use both velocity and acceleration. We'll get to that later, but it's good to have that in mind, that speeding up and slowing down, we'll have to use both velocity and acceleration to be able to tell whether it's speeding up or slowing down, because velocity is including a direction, speeding up or slowing down does not include a direction. So there's different cases for that. If you take the derivative of the acceleration function, I think it's called the jerk, but we're not going to do that. We don't get that far. In physics, you take the derivative and you keep going. Yeah, so those are the three main things. Just know if you start with a position function and you take the derivative, you get velocity. Take the derivative of velocity, you get acceleration. That's the key thing to remember from this little section. If you start with one, you take the derivative, you just climb up the ladder, okay? Or down the ladder, whatever you want to think of it as. So there we go. That's going to be the first video. Just short, a lot of wordiness, but yeah. We might start with an example next video.